For number 3, it says that your equilibrium constant for a reversible reaction A to B is 6. Conversion in a packed bed reactor is 50%. If a second identical reactor is placed downstream of the first reactor, what is the total conversion? So first of all, we know that the reaction looks like this because it's reversible. And we know that the equilibrium constant is 6. We know it's a PBR. And we know that X is equal to 0.5. So then, it's a bad drawing. So we have 1, and we want a higher conversion, so we end up placing another one downstream. And so we'd have a certain conversion here, which is given, and then we want to find this, so the total conversion. So first of all, we need to, since we're given the information for the equilibrium conversion, we want to write a rate law for this reaction and then find the equilibrium conversion from that. So if we assume first order, then we can start writing a rate law. So, and remember, the rate laws for the reversible reactions are slightly different from the irreversible reactions, because you don't have, in the irreversible reaction, you don't have anything reacting backwards, but in this case you do. So first of all, we have the rate forward, and since we're assuming first order, we can say that that's K CA. And then we have the rate in reverse, and this is positive since it's the rate of formation because it's going in the reverse direction. And that is K, this time it's that K, so the K minus CB. And then if you remember, we just combine these, so the total rate is rate net, so the minus RA forward plus RA reverse, and so that is equal to minus K CA. And remember, this is negative because of, let me write that right. This is actually, yeah, so then this is negative because this is the rate of disappearance, but the way it's written here, it's the rate of formation, so then that would have to be negative. So K minus 1 CB, and then we can pull K out. We want to pull out, well, first of all, we want to multiply this by a negative 1, so we get the rate of disappearance. So minus RA is equal to K CA minus K minus 1 CB. And then we know that, well, first of all, I'll pull out K. So minus RA is equal to K CA minus, and then since we pulled that out, we get K minus 1 over K CB. And then we know that this is Ke, well, the equilibrium constant, so K minus over K. And it gave us that, so we know that that's 6. But I'm not going to plug in 6, I'm just going to plug in the Ke right now. So we have minus Ra is equal to K Ca minus Cb over Ke. And then in order to find the equilibrium conversion, we know that when it's at equilibrium, the rate is 0. So we set this to 0, and then we solve for K. So setting this to 0, we get 0 is equal to K Ca minus Cb over Ke, so that goes away, and we get Ca equals Cb Ke. And so then we end up with Ke is equal to Cb over Ca. So then we need to figure out what Cb and Ca are. So, because what we're looking for is the equilibrium conversion. So we're looking for Xe. And so we need to write these Ca and Cb in terms of conversion x, so then we can solve the equation for x. So doing the stoichiometry, we know that Ca is equal to Ca naught 1 minus x, and Cb is equal to Ca naught x. This is assuming no volume change. So we can plug these in, and so we get Ke is equal to Ca naught x over Ca naught 1 minus x, so those cancel out. And then I'm going to write the x as Xe because it's the equilibrium conversion, so Xe over 1 minus Xe. And we know that this is equal to 6, so then we can solve it to get Xe is equal to 0.86. So now that we have this information, we want to go ahead and solve the PBR equation for conversion. Well, what are we solving it for? We need to solve the PBR equation so that we can figure out what x2 is. So I'm going to rewrite the rate over here because I'm going to erase all this. So minus Ra is equal to K Ca minus Cb over Ke, and also Xe is equal to 0.86. All right, so we have our rate, so we need, and we already did the stoichiometry, but I erased it, so I'll just rewrite that. So we know that Ca was equal to Ca naught 1 minus x. Cb is equal to Ca naught x. And so if we plug these into the rate law, we get minus Ra is equal to K Ca naught 1 minus x minus Ca naught x over Ke. And then we can simplify this a little bit, so this is equal to k Ca naught 1 minus x over Ke, and taking one more step, k Ca naught 1 minus x 1 plus 1 over Kc. And then, it might not be immediately obvious, but from the equation we had derived previously for the equilibrium conversion, so we had, I'll just write it down again, Ke was equal to Xe over 1 minus Xe. So we can just do some algebra, and if we rearrange this equation, we end up with 1 over Xe is equal to 1 over Ke plus 1, which looks like this. So then we can plug the 1 over Xe into this equation. So then if we do that, we get K Ca naught 1 minus x over Xe. And that's the rate. So from here we can write down the design equation for a PBR. And it is W, because remember, for a PBR we're interested in the weight instead of the volume. So the weight is equal to Fa naught 0 to x dx over minus Ra, and in this case it's, I'll just write that for now. So then, coming back to this equation again, you have the Fa naught is equal to Ca naught V naught, so we can plug that in and plug the rate in. So we get W is equal to Ca naught V naught dx over K Ca naught, because I'm plugging this in now, 1 minus x over Xe, and that cancels out. And we can pull K out, so then we have W equals V naught over K dx over 1 minus x over Xe. And I'm going to erase some stuff. So I'm just going to integrate this equation now, and this is, once again, either in the back of the book, in the appendix, in I think it's Appendix A, or you can solve it however you want. So solving that, we get W is equal to V naught over K Xe natural log 1 minus x over Xe. This is negative. And then this, if we combine this, so if we multiply this by 1, so Xe over Xe, and then combine it, then we get W is minus V naught over K Xe natural log of xe minus x over xe, and then that's equal to v naught over k xe natural log xe over xe minus x. And then we can rearrange this equation so we know what this is, and we know what x is because it tells us that x is 0.5 for the 1 PBR. And so we don't know the weight, we don't know k, we don't know v naught, so let's just multiply over k, divide by v naught, so then this is equal to xe natural log xe over xe minus x. So then we can plug in we can plug in xe and x and get a value for this. So 0.86 natural log 0.86 over 0.86 minus 0.5, and that's equal to 0.75. So we know that the weight times the rate constant, where the volumetric flow rate, is equal to 0.75 for this reactor. And so what it's asking for is the conversion out of x2. So we don't actually need to know what this stuff is individually to get that, because we already have this equation. We know what xe is, we know what this is, and we're solving for x. And if you remember, solving graphically for reactor design, you remember that in this plot you would normally have, say, FA naught over the rate by x, and then you would end up with a curve that maybe looks something like this. And then you remember for a CSTR, the volume of the reactor was something like this, like the area. And so the difference between, so this was for a CSTR, and then for a PFR, it was the area under the curve, so something like this. So in this case, with the PBR, it's the same sort of design equations. We're just looking for weight instead of volume. And so the area for a PBR, the area under the curve would be the weight. So then just looking at this, I'll erase the CSTR. So let's assume that the area under the curve right here, let's say this is our first PBR, so number 1, and then this is our second one, so number 2. And I know it said identical in the problem, and I know that this area is different, like these look like different areas, but just assume they're the same. So this is 2. So if you look at this, you can see that the volume or the weight is going to be the same for whether you have 2 smaller reactors or 1 big reactor. You're going to end up with the same. And this is the case with a PFR and a PBR. It's not the case with a CSTR, so just keep that in mind. So knowing that, we can say, okay, well, instead of having 2 reactors here, so we know that the weight multiplied by K and V naught is 0.75 for one reactor. And we know that for two reactors, the only thing about this equation that's going to change is the weight will double. So we can just multiply this by 2. And to get what this is for two reactors. So then we know that this is equal to this, so if we plug in if we say the 1.5 is equal to xe natural log xe over xe minus x, and we know what xe is because we already solved for it. It's 0.86, and so we should know everything, and we just need to solve for x. So solving this equation for x is equal to 0.7. So for the fourth problem, it says a first order reaction A to 3B is carried out in a batch reactor. So batch at 1 atmosphere, so P equals 1 atmosphere with 50% of inerts present, so 50% inert. And then it says the volume increased, so for this the volume changes, so volume increased 50% in T equals 10 minutes. So then it says in a constant volume batch reactor, so now you have a batch reactor that's constant volume, so this is one, and then constant volume batch. The P naught equals 5 atmospheres, and P, let's call that PT, equals 8 atmospheres, and this one has 40% inerts, 40% I. Alright, so then the question is, how much time will it take for the pressure to reach 8 atmospheres? So time equals question mark. So first of all, let's look at the design equation for a batch reactor. So design equation for a batch reactor is T time equals Na naught 0 to x dx minus RAV. And so we're going to need a rate law. So I'm going to also assume that this rate is first order. I don't think it says. Oh, actually it does. It says a first order reaction A to 3B. So rate, and I'm going to write first order over here. So then the rate is equal to K CA, and then we need an equation for CA, so I'm going to do stoichiometry. And since the volume changes in this, we need to account for that. So we have minus RA, oh, I already did the rate, So we have Ca is equal to, actually I'm going to use Na instead of Ca to start out. So this can also be written as Na over V. So for this I need Na, so, oh, and then there's K there, so Na is equal to Na naught 1 minus x. So then if I plug this into here, I get minus R A is equal to K Na naught 1 minus x over V naught 1 plus epsilon x. So theoretically you could have just taken this equation straight off the table, but I kind of wanted to show where this bottom part comes from. So this is because we're having a volume change. So, and the reason why this was V, so writing so I have this for that, Na equals Na naught 1 minus x, and V is equal to V naught 1 plus epsilon x. So that's where that came from. So before I continue with this, I want to take a step back to this real quick, because we're going to need this anyway. So this equation, V equals V naught 1 plus epsilon x, is actually this if I write the entire thing. So multiplied by P naught over P and T over T naught. So for this first reactor, it's constant pressure with the volume changing. So we know that P naught over P is equal to 1. And I'm also assuming isothermal. I don't think it says anything about temperature in the problem, so I think that's a good assumption. So then T over T naught is also equal to 1. So then we're left with V equals V naught 1 plus epsilon x. So that's where this came from. And then for this, so we just plug everything in. So we have the rate is equal to K Na, and I plug this in for Na, V, and I plug this in for V. And like I said, this is, you can just pull this off the table too, but I felt like in this case it was easier to write things down because we're going to be using this equation in a minute anyway. So then we want to plug all of, well, the rate and the volume into here and solve this equation. So going back to the design equation, we have T equals Na naught 0 to x dx, and then we can plug in the rate, so K Na naught V naught 1 minus x over 1 plus epsilon x, and then we also have V, so we need to plug in this equation for V. So we have, this is multiplied by, whoops, this is multiplied by V naught 1 plus epsilon x. So this V naught cancels out, 1 plus epsilon x cancels out, Na naught cancels out, and we can pull K out, so we're left with T equals Na naught over, wait, Na naught cancel out, sorry. T equals 1 over K the integral 0 to x dx over 1 minus x. So then we can just integrate this, and we end up with t equals 1 over k multiplied by the natural log. I'm going to write this a little bit different. The natural log of 1 over 1 minus x. So this is the equation we get to calculate the time for constant pressure, changing volume batch reactor. So looking at this, the question is, what are we looking for? So we're looking for the time in this reactor, but we don't have all the information we need. For instance, we don't know what K is, and so we want to get K from we have enough information from this reactor that we should be able to calculate K. So what we do need in order to calculate K is X. And so if we go back to this equation, we know that we know the volume change, so we know what V over V naught is. We know everything we need to calculate epsilon, so we should be able to solve for X. So we want to solve for X from this, and then we plug the X we get into this, and we know the time it took. It was 10 minutes, so then we can calculate K, and then we can use that K to solve this equation for the second reactor. So that's what I'm going to do. I'm going to erase some things. First of all, we want to rewrite this equation. So I'm going to write it as V over V naught equals 1 plus epsilon x. And then looking at this, well, first of all, we know that the volume increased 50%. So we know that V over V naught is equal to 1.5. And then we know that epsilon is equal to YA naught delta. And in this case, we know that it's 50% inerts. So YA naught is equal to 0.5, because if we have 50% inerts, then we have 50% A. And so this is the mole fraction of A in the reactor initially. So, and then we know that delta is equal to B over A minus 1. Yeah, that's right. So, and this is equal to 3 over 1, because the stoichiometric coefficient for B is 3, for A it's 1, minus 1, so that equals 3 minus 1 equals 2. So then plugging this stuff in, we have epsilon equals 0.5 multiplied by 2 is equal to 1. So then we know that, going back to this equation, we know that V over V naught equals 1.5 equals 1 plus X, because epsilon is 1. So solving this, we get that X is equal to 0.5. So basically, in the time that it took for the volume to increase by 50% in 10 minutes, so in 10 minutes you had 50% conversion. So then we want to take this, plug it into there, and solve for K. So going back to this equation, we have T equals 10 minutes, and that is equal to 1 over K multiplied by 1 over 1 minus 0.5. And solving this, we get that K is equal to 0.069 minute per minute. And I didn't write down, well, this is unitless, so you know that this has to be per minute. So now we have K, so we should be able to solve the constant volume. We should be able to solve the time required for the pressure increase in the constant volume batch reactor. And I'm not going to go through the math again for the design equation, but if you go through it, you'll find that you end up with the same equation because the volume cancels out. So I'm going to erase some stuff real quick. So I just want to rewrite this equation over here real quick because it's the one we're working with. So T equals 1 over K natural log 1 over 1 minus X. And so then looking at this, we want to solve for time, and we know K now. We just need to know what the conversion is. So we need to figure out what the conversion was in the reactor when the pressure increased from 5 to 8 atmospheres. And we can get that from this we can go back to this equation that we already used, the V equals V naught 1 plus epsilon x P naught over P T over T naught. And we already assumed it was isothermal, so that's 1. So this time, and we know that V over V naught is equal to 1 in this case because it tells us it's constant volume. So we know that 1 equals 1 plus epsilon x P naught over P. And so what we want to get is, we want to solve this for x. So we need to figure out epsilon, because since we have 40% inerts this time, epsilon will be different. So we have, just a reminder, epsilon is YA naught delta, and YA naught is equal to 0.6 in this case, because if you have 40% inerts, then you have to have 60% A. And then I already calculated delta as 2, but I'll just do it again real quick just so you remember. So it was the B over A minus 1, which was 3 over 1 minus 1 is equal to 2. So then if we calculate that, epsilon equals y A naught delta is equal to 0.6 multiplied by 2, and that equals 1.2. So then plugging everything into here, we have 1 equals 1 plus 1.2x. And then we know that P naught is 5, and P, the pressure that we're going to at that time, is 8. And then if we solve this for x, we get that x equals 0.5. So then we can just plug everything back in here and solve for time. We know K was this. We know X, so T equals 1 over 0.069 minute minus 1. Yeah, that's right. Natural log 1 over 1 minus 0.5. And so then solving that, we get that T is approximately 10 minutes.